Welcome to the Explainer. So if you're a focused learner looking to really grasp the foundations of how we measure and quantify the physical world, you are in exactly the right place. Today, we're demystifying the foundational math of chemistry. We're going to take what might seem like a bunch of dry rules and transform them into an engaging, high-stakes toolkit that you can actually use to decode the universe. We're diving deep into measurement and problem solving, and honestly, by the time we're done here, you're going to see numbers in a completely new light.
Okay, let's dive right into this. Here is our roadmap for today. First, we'll explore the certainty of uncertainty. Then, we'll tame unwieldy numbers, learn the rules of precision, adopt a universal scientific language, and finally, master the art of conversion. Each one of these concepts is an absolutely crucial building block for understanding the physical world.
So let's kick things off with Section 1, the certainty of uncertainty and the stakes of measurement.
In science, measurements aren't just dry, absolute numbers. They're actually a way to honestly report the physical limitations of our tools. Every single time a scientist writes down a measurement, they're communicating exactly how confident they are in that specific number. To see why this matters, think about a highly impactful real-world example. Why does reporting 0.6 degrees Celsius increase in global average temperature over the last century matter so much? Well, this measurement carries a critical degree of certainty, and it directly influences decisions that affect lives all across the globe. What's really fascinating here is that when scientists report this number, 0.6 degrees Celsius, they don't mean a perfectly exact 0.600. What they actually mean is 0.6 plus or minus 0.1 degrees Celsius.
In scientific reporting, the uncertainty is always indicated by the very last reported digit. So that 0.6 degrees means the rise could technically be as much as 0.7 degrees or as little as 0.5 degrees. But what it definitely tells us for sure is that it is not 1.0 degrees. The first digits are certain, but that final digit, that's always an honest, calculated estimation of physical reality, completely based on the precision of the measuring instruments being used.
Take a standard balance in a lab, for instance, which brilliantly illustrates exactly how this estimation happens. Imagine the solid red markings on the balance represent every 1 gram. When the mass falls somewhere in the empty space between the 1 and 2 gram marks, you have to mentally divide that space into 10 equal segments just to estimate that final digit. So if we estimate it sitting at 1.2 grams, we are totally certain about the 1, but the 0.2 is our estimated digit.
Moving right along to Section 2, taming unwieldy numbers with scientific notation.
The physical universe is just packed with crazy extremes. Massive quantities, like the number of atoms in a single drop of water, and incredibly tiny quantities, like the microscopic distance between 2 bonded atoms. To handle these extremes without losing our minds, scientific notation is our ultimate mathematical life hack. It takes a number and breaks it down into a manageable decimal part between 1 and 10, plus an exponential part. For example, if you have the number 5,983, you simply move the decimal point 3 spaces to the left to get 5.983. And because you moved it left 3 times, you multiply it by 10 raised to the positive 3rd power.
Now let's see how this works when we're dealing with the really microscopic stuff. If we have a tiny number like 0.00034, we just do the exact reverse. We move the decimal point 4 spaces to the right to create our number between 1 and 10, which is 3.4. Moving the decimal to the right gives us a negative exponent, so our final result is 3.4 times 10 to the power of negative 4. It essentially makes the totally unwieldy completely manageable.
That brings us to Section 3, the rules of precision, also known as significant figures.
Now that we know how to write these numbers, we have to know how to use them without lying about our precision. Think of significant figures as the grammar rules for our scientific language. They ensure we never accidentally overstate how precise our measuring tools actually are. Here's a quick rundown of those core rules. And I know, it looks like a lot at first glance, but I promise you it's entirely logical. It is all about tracking which numbers give us actual physical data. Non-zero digits and interior zeros, they always count. Trailing zeros count if there's a decimal point anywhere in the number, because they indicate deliberate precision. But leading zeros? They are never significant. They are literally just placeholders to show us where the decimal point lives.
There's also a really vital distinction we need to make between exact numbers and estimated numbers. If you're counting discrete objects, like knowing exactly 1 dozen objects means exactly 12 objects, that number has an unlimited number of significant figures, because there is absolutely zero uncertainty. But estimated numbers,
like a measurement of 2.9 times 10 to the fifth power, only have counted significant figures, in this specific case, 2. Why? Because they are inherently limited by whatever tool we happen to use to measure them.
And when we start doing math with these measurements, we have some pretty strict rules to follow. For multiplication and division, your final answer must carry the same number of significant figures as the factor with the fewest. So in a division problem where 5.892 is divided by 6.10, the first number has 4 significant figures, but the second one only has 3. Because of that, our final answer must round to 3 significant figures, giving us 0.966. The golden rule here, your answer can only ever be as precise as your least precise measurement.
On to Section 4, the Universal Scientific Language, the International System of Units, or SI. Okay, so we've got the rules of numbers down, but now we need the actual vocabulary of science, SI units. This is the universal language that guarantees a chemist in Tokyo and a physicist in Paris are talking about the exact same physical quantities. Take the standard of mass, for example. This is wild. For over a century, the kilogram was defined by a single physical block of metal, affectionately known as Le Grand K, kept securely under glass in France. Astonishingly, the foundational mass for the entire globe was based on this one carefully guarded object. And fun fact, over the decades, Le Grand K was mysteriously losing microscopic amounts of mass compared to its official copies around the world. As you can imagine, that became a huge problem for exact precision. But, science constantly evolves towards greater precision. Compare that physical block of metal to our modern standard of time. A single second is no longer defined by the rotation of the Earth. Nope, it's defined by an atomic clock. It is officially defined as the duration of over 9 billion radiation periods emitted from a specific transition in a glowing cesium-133 atom. I mean, that is the incredible level of precision we are operating with in the modern SI system.
Let's move to Section 5, the art of conversion through dimensional analysis.
All right, time to put the whole shebang together to solve some actual chemistry problems. We do this through a process called dimensional analysis. Basically, this means using units as a strict, step-by-step guide to solving problems. You just treat units exactly like algebraic quantities. They can be multiplied, divided, and canceled out. The absolutely crucial point here is that you should never, ever let units just magically appear or disappear in your calculations. They have to flow logically from the very beginning of your equation to the very end.
If you ever feel math anxiety creeping in, this 4-step general problem-solving strategy is going to be your best friend. Step 1. Sort. Figure out exactly what information you are given and what you're trying to find. Step 2. Strategize. Build a visual solution map using conversion factors. Step 3. Solve. Do the math and cancel out the units. And finally, Step 4. Check. Take a step back, look at your answer, and ask yourself, does this number actually make physical sense?
The fundamental formula we use is essentially the heart of our solution map. You just take your given information, multiply it by one or more conversion factors, and that equals the information you are seeking. Conversion factors are really just known equivalents, like we know for a fact that 1 inch equals 2.54 centimeters. Using these factors allows us to build a direct mathematical bridge right from our starting point to our desired answer.
Let's actually look at this bridge in action. Say we are converting 44.7 centimeters into inches. We multiply by our conversion factor, but notice how we arrange it so that the centimeters are on the bottom. Why do we do that? Because it is incredibly visually satisfying to see the given unit of centimeters completely cross out, perfectly canceling each other top and bottom, which leaves us with only the desired unit of inches.
Okay, let's test out our newly acquired scientific language with a highly tangible, real-world application. Think about this. Why would someone willingly pay more than $3,000 for a bicycle made of titanium rather than just getting one made of steel? Well, the answer lies in a specific physical property that we can now easily calculate and compare.
It all comes down to density. When we compare the two metals, titanium has a density of 4.50 grams per cubic centimeter. Iron, on the other hand, which is what makes up steel, has a density of 7.86. What this practically means out in the real world is that for any given physical volume, titanium has significantly less mass than steel. You get all the structural volume and strength you need for a solid bicycle frame, but it stays incredibly lightweight. And as we just saw, density is simply calculated as mass divided by volume. By understanding exactly how to measure that mass and volume with certainty, knowing how to convert the units properly, and respecting those rules for significant figures, we can confidently answer real-world questions like this. We've essentially cracked the code of measurement. So I'll leave you with this question.
What other physical mysteries in the universe can you decode now that you fluently speak the mathematical language of chemistry? Keep questioning, keep analyzing, and I'll catch you in the next explainer.